Let's now talk about the oxoacids of different compounds, their Lewis structures, and the oxidation states exhibited by the different elements. Let us first talk about carbon. These are the different compounds of carbon. First we have carbonate, which looks like this and has an oxidation state of +4. This is the bicarbonate ion like so and has a oxidation state of +4. This is the oxalate ion. It has an oxidation state of +3. This is carbon monoxide. It has an oxidation state of +2. And this is carbon dioxide. It has an oxidation state of +4. Now nitrogen has an array of oxidation states. For example, it has a -3 oxidation state exhibited in ammonia, the ammonium ion, and the amine ion. Now it will take time to find that. And it has -2 in the hydrazine ion. It has -1 in hydroxylamine. It has 0 in nitrogen. It's +1 in nitrous oxide. It's +2 in nitric 2 oxide. It has a +3 oxidation state in NO2 minus, N2O3, HNO2. This is a nitrous acid, and NO plus. And it has +4 in NO2, nitrogen dioxide, and N2O4. And it has +5 in NO3 minus, N2O5, HNO3, nitric acid, and NO2, nitrogen dioxide. Wait, what? No, this does not exist over here. What is that? And NO2 is over here. This is nothing. This is absolute nonsense. This is what hydrazine looks like. It has a -2 oxidation state. This is what hydroxylamine looks like. It has a -1 oxidation state. This is nitrous oxide with a +1 oxidation state. This is nitric oxide with a +2 oxidation state. This is the NO2 minus ion with +3 oxidation state. This is nitrogen sesquioxide with a N2 with a I think it has different oxidation states. Yeah, it has a +3 oxidation state. Nitrogen sesquioxide. Actually, this brings back memories because I had a legendary chemistry teacher. We call him CJ sir, and yeah, at the end of one class, like I approached him and I was like, wow, for the first time I heard of a compound by the name of sexy oxide, and he was like, no, it's sesquioxide. Yeah, sesquioxide. Repeat after me. Qui oxide. Sesquioxide. Your turn. Sexy oxide. Get out. Shoo. Yeah, it was a great. Oh, the good old days. Now this is nitrous acid with an oxidation state of +3. This is the nitrosonium ion, NO plus. There's a NO also. This is the nitrosonium ion, NO plus, +1 NO plus, and exists in this resonance state. This is NO2, nitrogen dioxide. You can see it has a day-tube bond and it can stabilize itself as N2O4 in the right conditions. This is what NO3 minus looks like. This is what N2O5 looks like. This is what nitric acid looks like. This is what NO2 plus looks like. This is what the ammonium ion looks like. This is what the amine ion looks like. And yeah, that's the chemistry of ammonia. Now we'll go to phosphorus. It exists as phosphide as in a -3 oxidation state. It can exist as phosphate in -5 oxidation state, and it can exist as phosphite in +3 oxidation state. And it has many oxoacids over here. It has the hypophosphorus acid with H3PO2 with +1 oxidation state. which looks like this. It has orthophosphorus acid with +3 oxidation state, which looks like this, and there's orthophosphoric acid which looks like this with +5 oxidation state. In IUPAC it will basically be phosphoric 1 acid, phosphoric 3 acid, phosphoric 5 acid. Now sulfur also exists in a repertoire of oxidation states. It exists in -2 oxidation state in sulfide, definitely hydrogen sulfide. It exists as -1 state in this compound, in this group. It exists in 0 in its normal form of sulfur and ground sulfur. It exists as +1 state in S2Cl2. It exists as +2 state in SCl2 and SF2, and it exists in +4 state in sulfur dioxide, sulfur tetrafluoride, and sulfide ion. It exists as +5 state in S4O62- and exists as +6 in sulfur trioxide, sulfur hexafluoride, and sulfate ion. This is what the per sulfide ion looks like. This is the per sulfide ion, -1 oxidation state. This is what sulfur difluoride looks like. This is S2Cl2. That's what it looks like. This is how sulfur dioxide looks like. This is how sulfur tetrafluoride looks like. Wow, it has an iconic seesaw shaped geometry. This is what the sulfite ion looks like. This is what the sulfur trioxide looks like. This is what sulfur hexafluoride looks like, and this is what the sulfate ion looks like. And we can go to the oxidation states of the halogens. So basically they exist in -1 oxidation state in chloride, bromide, iodide, as 0 state in the diatomic gases, and it exists in these various oxidation states as different oxoacids. You see, basically, like here we have the +1 state in HClO, HBrO, HIO. It exists as +3 state in HClO2, HBrO2, HIO2. It exists as +5 state in HClO3, HBrO3, and HIO3, and +7 state in HClO7, HBrO7, HClO4, sorry for my handwriting. It's HClO4 actually. HClO4, HBrO4, HIO4. Now most of these are pretty unstable, so they won't exist for a very long time without decomposing into lower oxidation state, but they are stable, and they are the oxoacids of chlorine. We got hypochlorous acid, we got chlorous acid, and perchloric acid in this oxidation state. This is what hypochlorous acid looks like. It has +1 oxidation state and is a weak acid, HClO actually. This is the chlorous acid or chloric. It has an oxidation state of +3 and is a weak acid. It looks like so. This is a Cl with 4 electrons. Then this is the chloric acid with a +5 oxidation state, and it's a weak acid. And it looks like this. And this is the perchloric acid. It has a +7 oxidation state. It's a very strong acid, and it looks like follows. Then we can go into the oxides of D-block elements. These are the oxides of chromium. They exist in +2, +3, +4, and +6 oxidation state. CrO is a weak acid. Cr2O3 is green and is amphoteric. CrO2 exists as a weak acid, and CrO3 exists as an acid. This is the oxidation states of manganese. Manganese exists as +2, 3, 4, 6, and 7 oxidation states. MnO is basic, Mn2O3 is a weak base, MnO2 is amphoteric manganese dioxide, MnO3 is a weak acid, while Mn2O7 is acidic. And we also have the oxides of vanadium. Vanadium 2 oxide is ash colored and basic. Vanadium 3 oxide is black and a weak acid. Vanadium 4 oxide is blue and amphoteric, while vanadium 5 oxide is orange colored and a weak acid. And these are the oxoacids and Lewis structures of various compounds of virtually the entirety of inorganic chemistry. And if you are interested about what these other junk is, this is the brown ring test. I will consider explaining it one day. These are the balanced chemical reactions of various oxidizing agents. This is how how nitrate and nitrites react with ammonia, with aluminium as a catalyst in a basic medium to form ammonia, and so on.